Think about how fast a clown car could go if we could harness the power of the sun to put into the engine. That's why today we're going to be brainstorming a fusion reaction powered clown car. Crap, this thing's barely gonna move.
It's always full of clowns.
He'd be late.
Okay,
He'd
no,
lose his keys.
Ding dong the clown.
That's the nerdiest joke we've ever had on
Both the hottest and the coldest place on the universe is right here on Earth.
So imagine that a group of clowns approaches you, probably when you least expect it, and they want you to help them build a fusion-powered clown car. So they want to wow the other circus performers. They're sick of feeling like the sideshow. Of course, we've all been there. And they have an unlimited budget, but they want to make sure that this engine has the power of the sun, is eco-friendly, and can pack way more clowns in than their previous car. Who is the group's leader?
Sylvester Stallone, you know?
Sylvester Stallone. First and last name of a Hollywood celebrity.
That's funny.
Yeah.
That's doable, yeah.
Right. I used to work at Gymboree, and so the clown's name is Jimbo, and we had to get into Jimbo and be a clown ourselves.
Okay, so Jimbo. Yeah.
Yep.
So, and he's probably rocking the whole shoes, the big hair, all that stuff.
I'm going to say Ronald McDonald is the CFO.
Oh, yeah.
Oh, CFO.
Yeah.
Oh, he is for sure. He's the financial.
Definitely.
He's backing it financially.
We got Wiggles the clown.
Wiggles. I like Wiggles. I feel like he'd always be late. He'd lose his keys.
So he'll be in charge of making sure that we have maximum power. Who would be in charge of making carbon neutral? What kind of clown cares about the environment?
I feel like it should be a play on Al Gore.
Yeah,
Clown Gore.
Oh, Clown Gore?
Clown
Gore. Clown Gore. That's
Clown Gore will be in charge
of
the environment. What kind of custom license plate do you think we should put on it?
Keep it simple. Clown power.
CLOWNPWR?
So much
Maybe we skip the O. CLWN.
CLWN.
PWR.
PWR. Yeah. Okay, cool. Decorations? What color do you think?
I think it should have a white base, just like a clown face.
Yeah, or it could look silly. Yeah, maybe yellow.
You add polka dots to it.
Oh, polka dots?
Yeah, and they have to be primary colors. And then maybe add like a fuzzy wig on top.
Oh, wow. This is
the
really
eyelashes?
changing. Those eyelashes.
Eyelashes on the headlights?
Yeah, I have. Yeah. Those car lashes? Oh, my God.
Yeah,
wow.
You have to put a fuzzy nose
For the
on
last few
front.
days, I've really envisioned something very different.
What I was thinking the whole time was like, if you went to AutoZone and bought every decoration and their custom spot, like little flames along the door, like pinstripes, like little tribal pinstripes.
Right. Every gas station where there's stickers, if you bought them all.
Yeah, exactly.
Right.
And put them all on this.
Like a bald eagle with like American flag wings.
Right.
All right. And last but not least, we need a bumper sticker for it.
You know how like you get the families and there's like the mom, dad, and then a bunch of kids?
Yeah.
Just put 20 grown men clowns. Like 20 grown clowns.
Just like man after man after man.
Yes.
And like a few of the silhouettes have like kind of the big shoes and
right.
like a few hair. Yeah.
There's like some baby clown.
But it'll just be the whole back windshield.
Yeah. Then it's
It might even be like two levels.
Keep going.
2 rows.
Yeah, probably will be like writing a sentence. It'll probably have to go down. Gio, why don't you tell us a little bit about what a fusion reaction is? I mean, I keep hearing that it's harnessing the sun, but like, what does that really mean?
Right. So essentially, in a big picture kind of way, the universe is a fusion reactor. Everything that we know is powered by a fusion reaction. And what that comes down to is the lightest elements in the universe that were made way back when the Big Bang happened. They are pushed together with immense gravity and immense power and heat to a point where they overcome the positive forces that the nucleus has. So, you know.
Okay, so I'm imagining like the very top left of the periodic table. So helium, right? Which
as
is
well as the
one...
top right. So top left would be hydrogen.
Oh, yeah, because it jumps across over there. Okay.
Hydrogen and helium.
So we start with a universe full of helium. Hydrogen.
Yep.
And that's the simplest thing.
Yep, one proton. Most isotopes don't have any neutrons and a single electron.
Okay.
So, but as simple as it gets.
You're saying there's a big universe of that, and then how do we get helium?
Right. So, after billions of years of these elements floating around, and they eventually start to clump up because of gravity, right? So as this clumps up for billions and billions of years, eventually you get a massive cloud. And this cloud accumulates so much mass that it begins to, become a sphere, and it'll push together tighter and tighter on itself. And when you have something as massive as a sun, it has so much gravity that it's able to overcome these internuclear forces. So if you imagine, you hear opposites attract, right? Well, positive and negative, they like to attract. An electron would be a negative and a proton would be positive. Well, protons and protons, they don't like to come together. They're both positive, they repel each other. So there's a lot of energy in that repulsion of each other. And when you can get something so hot and so pushed together, compressed,
right?
Yeah, they eventually become a new element. And that new element is helium. So now you have 2 protons and maybe 1 or 2 electrons.
So you're saying like if 2 people, like we're in a room and the walls closed in and then you lifted them out and then there'd be one person, but they'd be bigger.
Right. But at that same time, we had the mass of 2 people. You have to give something, right? So something had to be given up to be a person.
To squeeze them together.
Yeah. And typically in the fusion reaction, that's energy. So that energy can be harnessed, and essentially after the Big Bang, that's how all the energy and all the elements and all the isotopes that we know in the universe have come. And theoretically it can happen with bigger and bigger elements, but here on Earth, hydrogen and helium are about as big as we can manage.
I've heard we're all star stuff. Is that what you're talking about? Like,
exactly.
That's what you mean. It's
right.
like we all started as people being squished together to really big.
Right. So we're
not like people, but
we're mainly elements
stuff, right?
like carbon, hydrogen, oxygen, nitrogen. These are some of the most common elements in the universe. And if you look at them on a periodic table, they're all relatively low, right? 6, 5, 8, 1, 2. And typically the death of a sun comes from the fusion of iron. So once a star starts to fuse and create iron, that's what kicks off the death of a star.
So in a fusion reaction, if we have an energy source, are we going to keep going up that ladder? Or
Right. So if you think about what I was saying about the amount of protons coming together, the more protons you have, the more and more they want to repel each other. So these bigger and bigger these elements get, the more they want to push away from each other.
So getting all the way to iron is really hard.
It takes a lot of force, a lot of heat.
Is our sun even big enough?
So our sun hasn't, as far as we know, begun that decay process, right? That's when you'll get your
our
supermassive
sun's not even making
suns,
any of this stuff yet.
Right. We hope so, right?
Yeah.
But
then where's it getting its energy from? Because the
so
sun's
the energy
bright.
comes from the gravity pushing the hydrogen together. So at its most fundamental levels, it's fusing hydrogen and helium together, and the energy comes from it throwing away maybe a neutron or some gamma rays, which is another type of energy. And all these lights and energies is what we get here on Earth. We get UVs, we get visible light. Obviously, that's how we see everything. It's all energy coming from the core of these suns.
So for this clown car, that's what we'd be harnessing. We'd be taking all that extra stuff and using it to push the wheels faster and faster.
Well, I imagine it'd be like an electric car, right? So like you have a Tesla, like you get electric power, and your electric power goes to an electric motor that uses electromagnetic forces to turn the wheels. So if we can generate electricity with this reactor, then we can use it the same way we would an electric car.
So we can already start with we can take an existing electric car and we just need to replace the battery.
Right. Actually, we could keep a battery because you could store it. Unless you just wanted immediate power directly to the wheels. Otherwise, you have to have some sort of way to hold it and supply it.
This would almost be like the supercharger, and then people would bring their cars up to it. But we are just putting the whole thing right into it. So like a nuclear submarine, right?
Right, exactly.
We wanted just the car to be its own thing, powered probably for a long time on a little bit of fuel.
But a nuclear submarine, that's a fission reaction.
So what's the difference between fission and fusion?
So like I was saying about fusion, how you take the smallest and lightest elements on the periodic table and you push them together, fission's the exact opposite. You take some of the most dense and proton and neutron packed elements and you are essentially getting to a point where they're so unstable that they want to fall apart and become smaller elements. And we are just nudging them that little bit farther that they need in order to decay. And that decay, the breaking of those internuclear forces, they give off energy as well.
I didn't realize. So when because I was reading about the different things that you use for fuel, but the reason they choose those is because those are the ones that really want to fall apart.
Exactly.
Oh, so they're the easiest to work with. But
exactly.
You could work with anything. You would just need bigger and bigger.
Yeah, I mean, some elements are what we call stable, right? So they have typically an equal amount of protons and neutrons. But say you took an element that had 80 protons and you stacked 150 neutrons on top of it. It doesn't want to stay together. It doesn't have enough forces to keep it all together.
Gotcha.
So eventually it'll either throw away neutrons. There's different types of decays, but it'll start to fall apart.
Seems weird. So you get energy out of both breaking things apart and putting it together? Because it seems like one would take energy and one would give energy, but it's not that way.
The universe is really good at providing us with certain types of energy. So a sun is full of gravitational forces that are inherent to our universe, and it's already there. So the gravity might induce this energy, and that creates heat and the fusion reactions. But here on Earth, we don't have anything quite as powerful.
So gravity is actually the ultimate source of energy for the sun?
Right.
Because it's
so massive.
Right.
Definitely surprised by
Mind
that comment. But you're right, because I didn't think about that. And that's like twisting of time and space.
Right.
And we can get energy. Wow.
Typically gaseous planets like Jupiter, and they are what we call like failed suns. So they weren't massive enough to kick off a fusion reaction. So they're just these spinning balls of hydrogen just waiting for a little bit more mass for that gravity to compress them and kick off a reaction.
Gotcha. So maybe if we threw some rocks into Jupiter, then...
Right. Needs a little more oomph.
Then we'll finally have a two-sun system.
Right.
Like, what's the deal with carbon being dirty? Because it feels like we're made of carbon. I always remember thinking like carbon's awesome. It's got 4 and it like connects to everything.
Yeah.
But now it's always like people are like, I have a jet, but I pay for carbon credits. And like people are so concerned about our carbon footprint. But why is carbon hurting the environment when it seems like such an important thing to have? Or like who cares if we're making carbon?
So our atmosphere is relatively balanced, right? It has a certain percentage of gases, and it's able to keep our environment at the right temperatures. So if you think of a planet like Mercury, it's very close to the sun, and it's hundreds of degrees, maybe thousands of degrees on the surface, and it has little atmosphere. Something like Venus,
that's on the bottom of her mic. Do you know that?
Oh
yeah. By the way, this is Mars, that's Venus, and then you have Earth on the bottom. So you can use reference. He's the moon.
Gotcha.
But anyway, sorry to interrupt. Yeah. So tell me more about
a planet like Venus has such a thick atmosphere that it traps the heat from the sun, and it actually has a hotter temperature than Mercury. So when you have an atmosphere that's able to trap all the heat and the rays given to you by the sun, it increases the surface temperature of the planet.
Right.
So if we release carbon into our atmosphere, that's when you get this greenhouse effect. So it's trapping all the heat in the Earth's atmosphere. It's not letting it vent off into space.
Gotcha. So it's like adding more insulation to a house or something.
Exactly.
And so it's good, but then too much insulation, you're like sweating all the time.
Well, like on Earth, we have a very balanced ecosystem, right? Like if you throw it into sway a little bit by even a couple degrees, you could lose certain plant species, which tumbles down to losing certain animal species, and all that balance can just crumble in front of us. So like we might want it warmer because we don't want to shovel snow or whatever, but obviously that could turn into some pretty heavy consequences for our planet.
Jimbo is going to probably be concerned about what kind of fuel this takes and what kind of fuel is left over. What should he expect?
Right. So I guess in that question, we'll take it back, right, to why people think nuclear energy is so scary in the first place. So all the previous forms of energy that we've worked with, these fission reactions, they're using the materials that typically carry these scary names, your uraniums, your plutoniums, these ones that we always have to worry about. What do we do with the waste?
So this is nuclear powered.
Right, exactly.
Oh, okay. Even though it's fusion, not fission.
So if the power's coming from the nucleus of the elements, nuclear
so
powered.
Whether in or out.
Right.
Okay.
So we typically worry about this nuclear waste because, we're not super efficient with it. So it still can give off energy for hundreds of thousands of years. So, that can cause radiation poisoning and the like for centuries and millennia. And that's why we have issues with the waste, and it can run away. So that's why we have these reactions like Chernobyl, where, once you lose control of this reaction and it starts to run away from you, it's almost impossible to get it back. It's already began its process.
So there's atoms that are waiting to be broken apart, or like what is running away?
So
where there's more and more neutrons falling off of the same atoms.
Yeah, so what happens in a fission reaction is, say you split something and it throws a neutron and a helium out of itself. It's going to hit another atom. And you hit it with one more neutron, and it was just waiting to fall apart. And then that one throws a neutron, or maybe 2, and it hits 2 more. And then it hits 2 more, and
like when you're playing pool and you break, and all the one ball is like hitting all the balls, and they're
but now it
flying
can
everywhere.
Exponentially increase because you have, say, 2 neutrons bouncing off of each atom
until all the fuel is gone,
right?
Which is all the atoms that could be hit by it.
Exactly. So, and it's very hard to stop that reaction once it begins. Now, fusion, on the other hand, like we talked about, it takes a lot of energy input to the system. And if you stop inputting energy into the system, you've stopped the reaction. So the fuel on a fusion reaction are these light isotopes that we have all around us in a given day, your hydrogens and your heliums. Granted, some of them might have more neutrons than others. That's what we call isotopes. But once we stop inputting that energy, what you're left with is hydrogen and helium. And when it is fusing, you get helium and some neutrons. But ultimately, it's stuff that we have all around us at any given time, in the oceans, in the air. It's all already there.
So if the car got in a car accident, like what would happen with that energy? Where would it go? Like would a Chernobyl happen in that situation?
Yeah, we can't have this clown car like destroying.
Yeah.
Good point.
Yeah, like we have to evacuate the city because the clown car is in an accident.
Right. So no, the great thing about fusion reactions is it because it requires so much energy to control and to put into the system initially to get it going, that if you end those variables and you cut that reaction off, all you're left with is basic hydrogen that's full in our atmosphere anyway. So yeah, that's why we call it a more clean nuclear energy.
Oh, what do you mean by like gas?
Yeah.
If you compress a container, you're lessening that space in between every molecule that's bouncing around.
Right.
So that's how you would just jam more molecules into a given container.
Yeah.
Now, plasma, you essentially have ripped apart your protons from your electrons. You have a soup of these subatomic particles, just kind of
and none of them have
mixing
homes.
around.
They're just
right, and they're just waiting for something to be introduced. So you don't have
and they'll just find new homes as soon as they cool down.
So the protons are still positively charged, the electrons are still negatively charged, and they still would like to attract to each other and repel from each other as their charges seem necessary. But yeah, they're already stripped from their plasma, or stripped from their homes. So in the sun, you have a massive ball of plasma. That compression is much easier. You're compressing this soup instead of individual molecules. So in your car, you mentioned that you have a plasma. A fireball from the combustion of gasoline inside of your cylinder, that would be a plasma. Like this fire right here. Natural fire is a type of plasma. Yeah.
Wow, wait.
I didn't know that.
So we already actually have plasma in our cars.
It's the s'mores. It's like time to do plasma s'mores.
Right.
Yeah, plasma.
Don't we have plasma in our blood?
Yeah.
Yeah, exactly. That's a little bit different, and that kind of goes almost beyond my realm of understanding. But yeah.
I wonder why they call it that. Yeah, I wonder if there's some connection to the fact that your like hemoglobin is separated from something, or if it's like the same. I don't know about
Definitely.
that.
So Lex Friedman's dad is a plasma physicist and chemist and everything like that. So he has a great podcast with him, and he explains all sorts of things about cold plasma and medical plasma and stuff like that. So
This guy.
yeah.
Oh my gosh.
Very cool. So realistically, how fast is this car going? And
that's what I'm talking about. What kind of speeds are we going to be getting
can
here?
we get from 0 to 60? How long would that take from 0 to 60?
In order for a car to go fast, it has to have a lot of power relative to its weight, right?
Like really fast. Yeah.
Really fast. So when you think about your typical sports car, maybe in the 70s and 80s, you were talking 200 horsepower. So a really fast car in the 70s and 80s, maybe 200 horsepower. You got into the early 2000s, we were talking maybe 300 horsepower. Now we've reached a point of time where our engines are so efficient, we have 700, 800, 900 horsepower cars that you can just buy from a dealership.
I'm so excited to hear this number.
And
and what are we going to have?
Yeah.
What is the clown car going to have?
So if you go to the tokamak, which is one of the most popular fusion reactors in the world right now, granted, the world record right now for a fusion reaction is about 5 seconds.
Okay.
So we will...
Sorry, with 0 to 60, if we can do it under 5.
Right. So we will assume that this
and I'm sure we can.
power is made from some clown magic that is able to cool everything down at an immense rate.
Yeah, for sure.
So the tokamak at the minute generates about 16 megawatts or 16 million watts of energy.
Sounds like a lot of horsepower, though.
And it produces a 13 Tesla magnetic field, which is a pretty strong magnet. That's how it keeps everything together. If you convert that to horsepower, roughly 21,456 horsepower.
21,000?
Wow.
No, I'm not disappointed.
The tokamak is also
great.
23,000 tons.
Because we have the ratio of weight.
Right.
Oh, crap.
So
this thing's barely going to move.
So pound for pound.
What kind of clown car?
Man.
Pound for pound,
we put those racing stripes on it and that flame.
Pound for pound, if we were to convert that to the average engine weight, which is about 460 pounds for everything. That's 1/100,000th the weight.
Oh my
So
God. So a snail can out.
So
outrace this
1/100,000th.
thing. Oh.
That means that the average 400-pound engine is generating 0.04 horsepower.
Man, can you see how fast the snail moves?
Okay.
I bet we're not going to even beat
that's not
it.
be efficient to
No,
go
we're
to
gonna have to
McDonald's.
start.
No,
We're
no,
gonna
no.
have to start the circus, and it'll have to drive itself
The
out.
circus.
And that's assuming it scales, right? Like as if we could make a
Man,
1/100,000th
what if we got
reactor.
a couple of clowns to push it?
You might
that
have
help?
generated more horsepower that way.
Oh, jeez.
Yeah,
this thing's so
darn.
heavy. Oh. Okay, I got some facts on clowns we can jump to. An
Yes.
ASC is what they call it, American Standard Clown. Now, that's a 5'8", 158-pound person. They fit in 3 cubic feet, so 40
Right.
clowns should be able to fit inside of a standard clown car with 120 cubic feet. But in practice, only like 15 or 20 can ever do it because you got to
Wow.
breathe.
There's
and-
space.
I don't know. Yeah, because just
Then
like
you
those
gotta
atoms, you
breathe.
know?
Yeah,
like there's
exactly.
just, you can't just squish people into nice little cubes and like
Why
put them
not?
in there. But we could get up to 40. So I think we'd need to get at least more than 21 people in here too. So that's going to be additional weight, but probably
Yeah, exactly.
negligible.
Negligible to
compared how much,
23,000 tons.
Jeez.
Yeah.
Well, what if we cut a hole out in the bottom like the Flintstones and then they had some leg power
Love
with it
What
too,
do you think?
right?
Leg power?
That is definitely more than 0.04 horsepower.
What about all that space inside the tokamak? Can we put clowns in there, or are they dead?
Well, the internal temperature of the tokamak is about 150 million degrees Celsius.
Wow.
So they're fried in
Yeah,
a millisecond.
I was gonna go down. I was gonna say maybe some like shielding or a fireman suit, but it doesn't sound like that's gonna hold up
I don't
at
know
all.
if
If we could find some way to shield the tokamak, we would have a much longer reaction
That's
than 5
crazy
seconds.
how hot that is.
Wow.
So that
It's 10 times hotter than the surface of the sun.
why?
What?
Whoa. Oh, because the surface.
So wouldn't it melt
So
the
both-
car?
But that's the same temperature as the center of the sun. Yeah, wouldn't it melt the car? How do you? Oh, the magnets keep the heat centered or something.
So in
How
order
come
for
it doesn't melt the whole
cooling,
thing down?
we use superconductor magnets, and those also have to be chilled down to about 0.001 degree Kelvin above absolute zero. So we're
Wow.
using things like liquid hydrogen and liquid helium.
So you
to
need a
cool these
liquid
things down.
hydrogen garage to keep
Oh,
this.
jeez,
car
man. Yeah, it's
in.
got to be a
But that fun fact means that both the hottest and the coldest place on the universe is right here on Earth.
That is a fun
In the
fact.
center
I
of these
love fun
reactors.
facts like
Yeah.
that. The hottest and
The coldest.
Right? Is it still takes more energy to initiate the reaction than we actually gain from the reaction itself. Because we're using lasers and superconductors and vacuum systems and all these things that contribute to the energy consumption.
Yeah.
So if it generates 16 megawatts, it might take 30 megawatts to even power. So we're still at a net negative loss here.
yeah.
And that's why moving forward, some of the most exciting stuff is, how can we cool these reactors? That way we can keep the reaction going to a self-sufficient point like the sun. So
we can't just have the clowns like wait.
Right.
I mean, you
Cool.
might, yeah. How many clown powers is in a horsepower? What are we thinking?
Probably they seem kind of like they're misguided compared
Definitely.
to horses. Yeah, I feel like at least 4 per horsepower or
They're
something.
actually acting in opposite directions.
yeah, that's,
Right.
right. That's exactly the problem. They're like atoms. They don't don't
Exactly.
want to be next to each other. They pop out. Is that a good analogy? Like the way the clowns pop out of the car, is that similar to how the neutrons pop out?
Yeah,
of these
exactly.
things?
It's throwing
because
away
they're
a
all
neutron.
compressed into their
Yeah.
little thing.
The clown car was the nucleus, and it's losing a
Whoa.
clown or a neutron.
That's how they should teach it in school. Kids
Right.
would love that. Be like, all right, gaze up here, kids, because we're gonna watch a clown car. This is how an atom works.
Sweet.
Funny
But
enough, thinking about like the space in between these atoms, me and my buddy at work the other day were brainstorming essentially how massive a ball of solid neutrons would be. So we were thinking
job.
a 1 meter ball, and if it was essentially a neutron that was 1 meter, or
Yeah.
neutrons so compact that there was zero space in between them, we calculated the mass, and then without even thinking about bouncing that off of a known number, we were like, how much energy would it generate if we dropped it from an airplane at 10,000 feet? And as we were writing it down, we realized that 1 meter ball was more massive than the Earth was.
You'd never even be able to get the plane off the ground.
No.
No.
That's
But-
crazy.
You wouldn't even get to
That's
create it.
yeah. There's something really. There's a star that's really dense.
You'd end
White
the
dwarf or
world.
So
something
that's
like that?
that's when we realized that the ball that we were talking about was indeed a neutron star,
Oh, a neutron star. Yeah,
Yeah.
yeah.
and that if we dropped it from 10,000 feet, we would generate the same amount of energy that the sun generates over 3
so
seconds.
crazy to think about. Yeah, so if we had like a little marble and I drew it, it would just crash into the earth probably.
Exactly. And then we realized that if our ball 1 meter big was more massive than the earth, that it would actually be now the new gravitational center. So it's not falling into Earth. Earth is falling into this ball.
Like it would lift the
Yeah, exactly.
into it. Oh, that's so interesting to think about.
Hilarious.
So if you were just holding the little marble, the planet would just suck right up to it because that thing would be so big.
So
and
I think
suck
this,
me right into it and like that whole thing.
You know,
which if you just grabbed it, your hand would just go into it. It would just pull.
Well, this thing would probably be so hot and
yeah, there's a million things that would happen wrong
so many
with
things.
like your whole.
It would break down physics as we know it, essentially.
That is so interesting.
But
would it mess with time too? Would you be like, would you age less
Good possibility.
when you were standing? If it was like this big as that cup,
right? I mean, they say that
kind of like Interstellar. When you're
time differs the closer you get to a black hole. So I mean, I think a neutron star is as dense as we get before we're talking black holes. So
wow, you were such a cool guest.
I
love this stuff.
So how much fuel would it need?
Yes, that's really determinant on the size of the reactor itself, right? Like if we made it a 400-pound reactor, theoretically, it would require a lot less fuel than, say, the tokamak itself. But hydrogen is a very light gas. Say we put a 5-liter bottle of compressed gas on the car, that would probably last us quite a long time. Now, an alternative question is how much energy is required to start the reaction itself? And now we're talking, megawatt lasers, these lasers that would take all this energy and this heat source, and you need liquid hydrogen and helium to cool down the conductors. So
wow. So how many scientists would you say would need to be like mechanics on this car, like powered car?
It would require so many different industries to come together. I mean, just to generate the type of hydrogen used to power, you're going to have industries that can refine this hydrogen.
It does feel like we need like an international effort though with these clowns, because I know that ITER, which is one of the big reactors now, it said was like China and India and the like. You don't really hear like China, Russia, US very often, but they're all working on this technology together to help these clowns.
Right. Yeah, ITER is going to be super cool. That's supposed to take all the numbers I gave you about the tokamak and multiply it by 10. So
when would we expect this car to be delivered? Because obviously Ronald and Clown Gore are all going to be
it's a good question.
ready to show off to the other clowns like, hey, check it out. We got the new Fusion car.
Right. So fusion technology has been in the whispers for decades now. And
so it must be around the corner.
We would think, right?
Oh, yeah.
ITER's supposed to open in the next couple years. So maybe with some of the technology that ITER gives us, we could use some of their superconductors and their technologies and scale it down and let them dump the billions of dollars into it.
It's about 2 more years, you think, until that kind of prototype is generating energy. Maybe 2-3 years. So then you think we're pretty much right away we could all start building in different countries, ones that are actually useful? Or is there like something that's going to not make that?
Yeah, I don't believe that there's any plans to have a bunch of them. I think ITER is kind of like everyone's contributing to it. And this will be the primary reactor for quite a while. But I think once we start to figure out the science and we can mass produce things cheaply, efficiently, and we can kind of get everybody coming together on the idea that nuclear power doesn't have to be scary like we've been told our whole lives. We're not Homer Simpson kicking our feet up, eating a donut at the reactor.
Ruined it for all you guys.
Yeah. And hopefully in the next coming decade or so, we could start to see some real changes with power generation.
Do you have any like Homer Simpson memorabilia at work? Do you like in the cafeteria or anything? Yeah,
for us, we do create fusion reactions, but we often don't think about it that way. We think of ourselves as like pulse power, neutron generation, like these really fast pinches. I mean, our reactions are lasting microseconds. So our job isn't to create this energy source. Yeah.
But this clown car, is it only realistically now it's only going to go forward at a snail's pace for 5 seconds?
Exactly.
Oh God.
Unless
that's what we're dealing with here.
Here's my thoughts. I imagine a clown car is almost like this portal into like a greater space. Okay. Like in Harry Potter, if you ever seen like them walk into their tent and their tent is like a full blown like house inside of it. Yeah. Like that's what this clown car is. So maybe we can just fit the entire 23,000 ton reactor inside of this little car.
That's true, because the clowns know how to squish things down
Exactly.
in a way
They
that maybe
Right.
even the sun doesn't, and keep everything spacious inside.
Maybe
So,
they need wizards
Who
too.
knows?
You
Yeah,
know?
who knows what the clowns already know? I mean, they've already been doing something
Right.
Yeah.
that we don't understand.
I know sometimes.
Maybe they teach you at a clown college about some sort of physics that we don't learn in like regular college.
Definitely.
That is so true.
Wow.
Okay, so it sounds like it's going to be kind of expensive. I know it cost about $20 billion so far for ITER, for ITER. And as a reference, I looked it up, and there's $120 billion that went into getting us on the moon. So do you think now that we spent $20 billion, we can get the rest of the way for less than $100 billion more?
Well, how does that scale, right? Like, is that 1960s dollars or is that adjusted for inflation?
I probably didn't convert them correctly, but
if I know anything about government spending, it tends to rack up pretty quickly. So, maybe sub 100 billion. That's a pretty good price point for us.
do you think we can budget that for Ronald? Probably under 100 billion for will probably be deliverable.
Everything initially is expensive, right? Like if we let them deal with all the expensive R&D type stuff, we might just be able to like, oh, thanks for the idea. And we just start throwing it in. I mean,
that's true.
Maybe we train them to make their own superconductors and magnets, and
maybe that's where all the other countries come involved. They
it's
can
true.
help with
Different
finances.
currencies. Yeah, who knows?
Exactly.
We could pay them an entertainment value too with our clown car. Be like, you all get free tickets, everyone in your country.
Of course.
Come check out the show. Actual nuclear fission is getting safer, right? Because there's different generations of reactors. So do you think maybe this is a kind of wasted energy and we should just stay with the radioactive stuff because we're getting better at securing it and storing it and all of that?
I think moving forward, our idea of energy will be very different. It'll be very multifaceted. Maybe 15% solar, 15% geothermal, 15% wind, something like that. And I think fission is here to stay. I think once we start becoming more efficient with getting power out of, every bit of material that we can, instead of 10%, 15%, then it'll be a much safer place in people's hearts. Like, I think the thing a buddy of mine told me was a gram of uranium, if you were to extract every single piece of energy from the entire gram of uranium, could power a city for a day. So, and you're talking material.
Getting more efficient with that.
Right, and we're talking material size of a penny. So, like, if we are able to get efficient, a 55 barrel drum of, say, uranium might be able to power a country for a day. Something
and even
like
if it's radioactive, if we have good controls around it, then maybe that's still
right. And if we exploit it down to where it's decayed to its absolute smallest form and it's just a barrel of lead, then maybe we'll be able to dispose of that a little easier.
Or like, what kind of materials should we build it with?
There's a satellite that's orbiting the sun right now, and it has an insulative material on the outside that can dissipate heat so well. There's a guy that, he puts it in a furnace, 1,000-degree furnace, pulls it out, and he's holding this glowing red cube of this material because it's
not burning him?
It's not burning him. It's just dissipating the heat.
We need that material.
So that's the kind of thing.
That's
whatever that is what.
Yep.
Sense, like, how would you describe heat dissipating in different materials, or like, what should I even be thinking about when I'm thinking about something that burns me and
so
quickly cools off? Like, what's happening in the subatomic particles or something?
Yeah. So all matter has heat. Even ice or liquid nitrogen, like, we think of these things as very cold. They have heat. They're just colder than us. So anything above absolute zero has heat. So all heat is a difference in energy from one thing to another. So when something has more energy,
it's only relative to something else.
Yeah, typically we refer to absolute 0 degrees Kelvin, or negative 273 degrees Celsius or something like that. But that is at a point where all atoms would just stop. They don't do like the vibrating that they normally do.
They just chill.
They just are completely dead solid.
Do they like that?
No. That is
they want to move. Yeah.
Right. As of right now,
that's need to like move around a little bit.
As of right now, it's a theoretical number. I don't think anybody's ever actually reached that. So we'll typically go 0.000 to the 99.01 degrees Kelvin. But so everything has heat, and some things are able to dissipate or trade off that heat better than others. So that's what we call like insulators.
Yeah, so that special material is somehow quickly taking all of that heat and just letting it break apart.
Yeah, throwing it off into the air.
So I will throw out, though, that the current world record for the clown car was made in 2013, and they were able to fit 31 clowns in a small French town into a Citroen 2CV. Can you look that one up, Matt?
Yeah.
I'm curious what that car looks like. But that nobody's been able to break that, even though it's been attempted. So do you see a fusion reactor being able to fit in that engine?
Sure. I mean, ultimately, it's just a vacuum chamber with some gas pumped into it and, some magnets.
And a 1,000,000 temperature.
Right. But
doable.
temperature is not, a dependent variable to size. Like, it can get super hot and be almost
Very
microscopic.
tiny.
Yeah.
Okay. So as long as you have the right materials and we figure it out.
But I'm not sure how that power scales, right? Like, what if I want a 400 horsepower engine? It would have to generate a lot more power per cubic inch of.
Wait, would it still
fuel.
be super heavy, or do you think we can drop the weight if we get small enough?
No, I mean, I think that a lot of that weight is because we're talking, the room is as big as, the studio here.
Yeah.
So massive, and it's full of heavy metals and magnets and liquids.
Okay, so maybe one day we get it that small.
Yeah, I think so. I think moving forward,
has in the car.
imagine like in the 1940s, they gave you this computer and they were like, hey, this is a pretty powerful computer. It's about the size of a room.
Interesting.
Yeah, it's about the size of a room, and you have to program it with strings. And now we have, a more powerful computer right here.
So a spaceship maybe?
Right.
Powered by this thing, and then it could land, because it only needs water, right? So it could land on an asteroid, grab some ice, and refuel?
Yeah. I mean, have you heard about like the moon helium mining?
No, tell me more.
So there's essentially on the cold side of the moon or the dark side of the moon, it's just been bombarded by, space gases for millennia. And they believe that there's a buildup of helium on the surface of the moon.
Okay.
So the logic is that we could potentially mine the moon for helium. And I think that the same would go probably for these hydrogen isotopes.
Hey man,
if we're already
a great
up
way
there,
to build a spaceship then, huh? And
get it there and then just fill up with
of course they could always dump radioactive stuff out the door, but still,
yeah.
I'd rather,
if we could figure out how to fuse helium relatively efficiently, we might just be able to get out there with enough fuel to get there, fuel up on the dark side of the moon, and get back.
Man.
Wow.
Funny.
Like that idea.
How would that affect the moon though? Like, does it just keep producing the helium, or
But the
what,
helium
what is
it
that?
won't float
No,
anymore.
it's definitely not a
All under Earth.
renewable resource by
Right.
any fast means, but I imagine it's similar to Antarctica. Like, we have this Antarctic treaty that like we're not allowed to mine or colonize Antarctica essentially.
Yeah.
So maybe the world will just come together and decide like, hey, we're not going to just completely ruin the moon. That's my hope anyway.
You think we make it another 1,000,000 years as humans?
Probably not.
Oh, maybe not.
I'm kind of a pessimist in terms of that.
10,000 years?
I don't know if I give us another 5,000 to be.
5,000?
Yeah.
Where are you at?
Yikes. Well, I just learned about that theory of the universe like closing in on itself, just like how the Big Bang
Or
like,
pulling
began-
apart, right?
Pulling,
is that what you mean?
Is that what it is?
Yeah, it's pulling apart.
It's pulling apart.
Yeah. That's dark matter. It's just pushing us apart. But don't worry, Einstein didn't believe in it either.
Really?
Yeah. He was like, he called it the cosmological constant, and he said it's just a thing I have to do to make all the math work out, but it's not real. And then later people were like, oh, there's actually dark matter pushing everything apart, and you discovered it, but you didn't believe in your own equation.
Really?
Yeah.
Have you ever seen these dark matter like laboratories out in like Antarctica?
No,
and, like,
there's a dark
underground?
matter laboratory?
It's considered
Oh,
the most expensive material in the universe because it's like billions and billions of dollars for
is it even-
micrograms.
Yeah.
But
We can even do that? We can even
so I think we're
contain
more
it
like
or hold it?
detecting it more than anything, but it's underground, like a mile underground, where eventually everything kind of like you can't get any
Settles,
rays
sort
from
of?
the sun or like any sort of background radiation or anything, and we're just kind of detecting these little pieces of dark matter just ripping through the earth because they go through the
wow.
earth without any problem.
Yeah, they just come right through it. At your facility, do neutrons, are you worried they're going to go through you and hurt you, or do they just go through you and not hurt you, or do you guys contain them somehow?
No, so neutrons have a time of flight. They have some sort of mass, so they'll eventually fall off. But we take our precautions. The thing that we like to say is 1/r². That's the formula for when we become safe. So
Okay,
like the
gotcha.
radius away from the source squared, as you increase that
Means
radius.
every step away makes a big difference.
Exactly.
Yeah.
It's exponentially great. So we keep our distance. And then neutrons, what makes them awesome is they'll fly right through lead, steel, all these things that contain normal things, but they are really attracted to hydrogen. So a barrier of water or a plastic, a poly, anything like that is really good at stopping neutrons.
That's interesting. So is that your favorite, or rank your subatomic particles by favorite to least favorite?
Ooh, favorite subatomic particles. Are we going like subatomic, like
sure, yeah,
quarks and gluons?
Sub as you want to go.
I'm gonna go number 1, gluon. holds everything together.
About a gluon. Tell me why?
It holds everything together.
Oh yeah, glue.
Gluon.
Oh, okay,
yeah.
Should've known that.
So I'm just gonna say that keeps us all together. Gluon, pretty appreciative of it.
Higgs boson.
Ooh, now we're going to God particles.
I don't know. Is that that's not your favorite? You like the gluon more?
If we start to really find out for sure what started the universe, it takes away a lot of the fun of science, right?
You like the mystery?
Yeah, I kind of like the mystery. So yeah, Higgs boson, that's cool. That the God particle is what we like to call it. It's what they believe might have kicked off the Big Bang, but
neutron, proton, electron are not even in your.
I'll stick to.
Are those two mainstream?
Okay, so I'll rank the basic 3.
Okay.
Maybe 6. We'll do antimatter as well.
We need the antiparticles, of course. That's a whole different list.
So
the
number 1
list and the particle list.
Number 1, electron, because electrons do some really cool stuff, and it affects everything about that atom. It affects how it binds, how it charges, how it gives off energy. Number 2, neutron. Mainly because I work with it, I'm a little biased, but also because
they're your guys.
It took so long to discover it, because it has no charge.
No mass. Or no charge. Yeah.
No charge. So we were able to identify protons relatively easy. Everything had to be made of something. Electrons, we realized things had charges. There was this negative counter subatomic particle to the proton, but neutron is just this proton, probably number 3. But
okay, so you have the big ones in there.
Yeah, but antimatter's cool.
What's exciting about the proton?
That's why it's number 3.
Yeah, I see what you mean.
I mean, everything about a single proton makes up, the chemical properties of everything, right? So what makes
got that going for it.
Yeah, what makes hydrogen and helium different? A proton.
Yeah.
What makes,
it's the way to stand out.
What makes tungsten and steel
different? It's the way to stand
different?
out in this world. You add a proton, you take a proton away, you're different.
Makes a completely new material.
Yeah.
All cool stuff though, so it's hard to say.
Yeah, but
I think that's my list. Electron,
and
neutron,
what about
proton.
the antiparticle list?
Just take that list and flip it. No, I'm just kidding.
That's the nerdiest joke we have ever had on this show. Just take it and flip it. Of course, because it's anti.
Yeah.
That's a good one.
No.
Ooh, that was sharp. That was sharp, man. I don't even know how you rate the antiparticles, because we don't really know a whole lot. Do much with them.
Yeah,
right?
I truthfully don't know if a anti-proton, I forget what it's called. Is it?
Because there's a positron, which is the opposite of
an electron. Right.
Yeah,
antiproton.
Okay, so it is an antiproton.
An antiproton.
Cool stuff, though.
We just came up to the edge of our knowledge, which is perfect. Which is right where we need
ourselves
to be.
out.
Yeah. Right where we need to be. But I think that's good. Any other questions?
No,
that was really fun. Thank you for coming and talking to us.
Absolutely, I had a blast.
Yeah, this is exciting, and I love. It must be so fun to just work with those guys and think about this stuff all day. So, I'm glad you were able to bring a little sampling of that.
Absolutely.
Okay, let's do it.
Do it.